All right. I'd like to introduce our next speaker, who is Mads Torgersen, who is the C# language PM. He's also the Lang.Next conference organizer, and he very cleverly reserved a slot for his own talk. However, fortunately, he has a very, very good topic to talk about, which is the asynchronous programming model in .NET, which he was a very large proponent of and really helped drive this feature both in the language and in the CLR and in Windows.
So I'll try to do the thing you should never do and talk and try to solve problems at the same time. So I want to thank Martin for setting me up beautifully by showing one example of where asynchronous programming has become really core, all while I'm changing my refresh rate here. So obviously we want, is that better? Yes, perfect. So obviously we want C# to be a great language on Windows. That is one of the goals of starting to tackle asynchrony in a first-class manner in the language itself. But there's several other scenarios for that. So let's start out by talking about. Clearly, this is a list of stuff we've been doing in C# over the next releases. Since after 2.0, it's pretty much been not so much about rounding out the language itself, although there's some of that, but it's pretty much been about how does the language interact with the rest of the world. It's about C# being used in the real world, being used to bring queries into the language itself, being used to target things that are not in the .NET type system through dynamic. And the next thing is really dealing with the fact that we're in a distributed world. There's a lot of latency, much more latency in the world than there used to be. And that always makes the programming experience difficult. So we want to tackle that by supporting features for asynchrony in the language. And what is asynchrony for? Well, primarily two things. You saw the talk just now focused on responsiveness. So if you're in a client app, you don't like it when you get the spinning donut or whatever the Mac equivalent of that is, when something is doing something on the only thread that can update the UI, especially when that something it's doing is staring down a pipe, doing nothing but waiting for something to come back. Right? You don't want to block your UI thread, and you don't want to hog it doing CPU-intensive stuff, because that's a precious thread that it's the only thread that can interact with the user. Right? That should be freed up as much as possible to interact with the user, and that's the responsiveness aspect. The other one is that in our imperfect world, threads are expensive, and so if you're on the server side, if you have a middle tier or whatever, you don't want the number of threads you allocate to jobs being the bottleneck for how many requests you can serve per second. Right? You don't want that to be a bottleneck for throughput. And in many situations, if the way you handle requests is, you get a request, you turn around, you ask somebody else for something else in order to federate a request, most of your time, again, is spent staring down a pipe waiting for that stuff to come back. So you don't want to hog a whole thread for that necessarily. And asynchronous programming, again, is by now sort of the recognized medicine for these scenarios. The only problem is that asynchronous programming is kind of hard. Always involves some kind of callback-based programming. In order, you sort of want to get off your thread so somebody else can use it for a while, and then provide a callback for what should happen whenever you're ready to do some work again. And that kind of makes it hard. One advance that has been is sort of there's a bunch of future-like abstractions that are gaining traction out there that are better abstraction over ongoing stuff that I'm not working on right now, but somebody else is, and then it will eventually come back to me. And that's also the basis for a lot of the async work. The async work that's being done in the Windows runtime, JavaScript promises, and also what we call tasks in .NET, which I'll focus on in this talk. Just to address some, there are different terms around for different things that are very closely related. Some people talk about promises, some people talk about futures. They're all objects that are essentially they're sort of reified representations of ongoing activity, and they help you separate the initiation of that activity from the consumption of the eventual outcome. Actually, this is perspective I got from Claudio's talk on Friday. It's a very good way of thinking of it. So you can kick something off. You can get a placeholder, a first-class object that then represents your ability to eventually consume the outcome of the operation once it's done. Okay. Now, there's sort of the classic notions of futures and promises are in different domains. Futures are sort of classically something from concurrent programming where the activity that you're abstracting over is CPU bound, so you're doing some really hard work on a thread somewhere and you kick another future off and you have some really hard work on another thread, and it's all about coordinating those. And so your typical workflow will be when you eventually consume, you do that by blocking until you get the results out of that. Okay? Whereas promises, as known from JavaScript, for instance, they're more about I/O bound work, so they represent something you asked for over the web or whatever. And the way you consume them typically is asynchronously, by giving a callback saying, hey, you know what, when you're done, could you please do this afterwards with the result? So they're sort of different in that sense, but they're easily unified, and in .NET we use the same type for both concepts. We sort of just merge them together. You can really separate one axis about what kind of work it's doing from the axis of how you're consuming the eventual result. And that's a little dangerous. It's not completely, I mean, it's easy to do from an API standpoint, but it's not completely safe because you can imagine when abstracting over I/O-bound activities on a single thread, and if you start consuming by asynchronous waiting, you can get deadlocks on yourself and stuff like that. So there's a slight danger in that, but we think the gains are significant from having a unified view on this, and I hope to make that point later. So if we look at synchronous versus asynchronous programming here, I have two versions of little snippets of code. One is ordinary synchronous. I call a download method. It takes some time. My thread is blocked. This bar here is the thread. My thread is blocked for that duration of the time, and I can then come back and process the outcome later. But in between, my thread is blocked and your donut is spinning. Whereas the asynchronous version here is a little more complicated. I'm getting a future back of some kind from an asynchronous version of the method. I get that immediately as I make the call. It gives them back, here's your ticket for when we're done. We'll call you when you're done. And you can then sign up a callback with a Lambda here to some kind of then method or continue with method or whatever. And that complicates your work, but it means that you're only actually occupying the thread for when you're doing actual work. And other stuff can happen. Say it's a UI thread. You can interact with the user, events in and out, be responsive. Whereas all those events would come after. You know this feeling when you've tried to get in contact with your UI for a while, and all of a sudden it all replays in fast forward. Another aspect of this is concurrency, and I think that's an important aspect as well. You can have just one thread. You can only do one thing at a time. So if you want to do 2 downloads, you do them one at a time sequentially. Whereas in an asynchronous world, you could kick off 2, and then you could do the callbacks a little later, and your time to last byte is much shorter. Right? So just the sheer concurrency on a single thread is very useful here. So now I set the stage, and I'm sort of more into going into code, so I'm going to go into code. And I'm going to show you what the language aspect is of this. So I mostly talked about why asynchronous is good, so I'm going to start out by telling you why sort of normal callback-based approach to asynchrony is what's problematic about it. So here's a little app, and I'm going to run it, and hopefully it'll run, compile, run. My machine is a little slow. So this is a little app. Some of you may have seen it before. It will go search for movies on Netflix. If I click the search button, so this is sort of a non-responsive app. I can't move the window. I'm trying to move the window. I can't press the cancel button. But eventually, it'll come back having sucked down a bunch of movies from Netflix, and it will do all the updates in one go. Right? So that's the experience we don't want. We don't want the UI to just go away while we're trying to talk to the user. So if we look at the code, though, it's pretty nice. It's very intuitive. You have a method here that's an event handler. When you click the button, call the event, it just parses up the year you gave and calls a helper method called load movies. And Netflix wants you to give a particular chunk size at a time, so we kind of have to loop and know Is there more data? So we have an outer loop that loops and asks Netflix for the next chunk of movies. Here's the loop. It's got a try-catch around it in case something goes wrong. And the work is really done here where we query the movies in another helper method. So let's go look at that. And that helper method returns a movie array of the next 10 or 20 or whatever movies. And again, it's pretty simple, straightforward sequential code here. Then the important thing is that we download a string, and that takes time. And it's a blocking operation. So this is where the culprit is. We're doing a blocking web access. We do it in a loop, so we're going to be blocking multiple times, all while keeping everything else off the UI thread. So this is what's bad about it. But it's really, and then after we get the data, we will do some work to parse the string as XML, put it into movie objects into an array, and we're done. Easy to read, doesn't work so well. So let's look at what the asynchronous version of this could look like. And let's start with the culprit here. Let's start with talking about what should an asynchronous method look like. So if I wanted to do this asynchronously, I just talked about tasks being a good way to express or abstract over things going on at the same time. So a good asynchronous method is probably really one that returns you a task, right? It kicks something off and returns you a task. So what we're saying that asynchronous methods should look like in .NET going forward, we haven't always said this, but we're saying it now, is that they should return a task. And then just for the benefit of readability and for convention, you put the async postfix on the method name, and now you have a signature that clearly states, I'm asynchronous, I'm going to give you immediately a ticket to the eventual result. That's what a method should look like, okay? Now we can do stuff like you would do in JavaScript, where we call another asynchronous method. So this one, for reasons I won't go into, it's called download string task async, and you can see the IntelliSense is telling me this is an asynchronous method. It's returning you a task of string. So immediately you call this method, you get a ticket back to a string in the future. Well, that's good, because that means I can go and sign up a callback. So let me call this one back. There's a continue with method on tasks that lets me take the rest of this method as an action, as a lambda, and have that happen as a callback. So let's see. First of all, let's get the data in there, and I'm going to actually what it takes is a continuation is something that takes the completed task, and then I can ask that task for its result. Okay, and now I know the result is there, so this is not going to cause any blocking or anything. Now I have the result. I can start working on it and eventually return it. This is all in a callback, so I have to close out the call to continue with here. And all I need to do now is to return the result of continue with. So there's an interesting, tasks are really nice, and that's the same thing with promises in JavaScript, in that you can give them some work to do, and then they'll return you another ticket for the completion of that work. So asynchronous, the composition of asynchronous methods is really nice that way from an API point of view. You just create new promises all the time. So this wasn't actually half bad, right? All I had to do was wrap my code in a little bit of Lambda goo, and we're sort of used to that. We can take that. The problem really is that the method I had was deceptively simple. It was just straight line code, and the problem really comes up when I'm in a more structured situation. So my sequential composition in our beloved imperative languages isn't just about semicolon, right? It's about having control structures and having ifs and whiles and exception handling and all kinds of advanced stuff that helps control what happens in which order. And once you become callback based, it's amazing how much of that just goes right down the drain. Okay? So let's say I call query movies async here instead. Now I get a task back. Well, okay, I guess that's fine. I'm going to call continue with on that, continue with, and then give it a lambda with the rest of what happens in this method. Well, how can I give it a lambda with the rest of what happens in this method when, if I could remove the IntelliSense here so you can see the code, just a few lines down, I'm ending the while loop and going around one more time. How do I capture the going around one more time? I guess I could do my own manual continuation passing style transform on my code, right? So I could say, okay, let's not use a while loop. Let's make some kind of lambda that signs itself up for the next iteration. If it needs to go around another time, it signs itself up. How do I deal with the exception handling that's around it? Well, maybe I can sort of tag that on the end somehow, and I have to turn my code inside out. Right? And this is really where it gets hard. So when code gets structured, when your synchronous code would get structured, your asynchronous code gets unstructured or horrible, right? So that's a problem that we're trying to address here. Now, I want to back out of what I did and tell you what we're doing instead. So if we look, let's go forward a little bit. Let's see, where am I? So if you look at the query movies method down here, I still want it to be, I think the signature that I had was right. I still want it to have the signature here, but I want a better way to implement asynchronous methods. And that's where the language comes in. That's where API can't help us anymore. So if we start looking at what's the compiler telling me about what's wrong here, it's saying, hey, you're returning the wrong thing. Well, I can fix that. If I go to the compiler and say, hey, compiler, this is really an asynchronous method. Okay, so I put async in front of it. Then the compiler says, oh, all right, you're an asynchronous method. That means one of my jobs, apart from a number of other jobs I'm going to tell you about in a minute, is to help you by creating a task that you can return to your caller. Okay, so I'm creating a placeholder for you, just free of charge. You just have to pay those 6 characters up there, one of which is a space. Oh, that's nice. Thank you. Okay, so now the squiggle went away down there. It's actually fine what I returned. We got another squiggle. It's only green because this code is actually fine. But there's one problem with it, and that is that it's not doing anything asynchronously, so it's not really helping us. I'm still doing the synchronous download string here, so I'm going to go and do what I did before and get this task back. And now I'm now at the place where I would introduce this callback. And what I'm going to do instead is use a piece of utter magic that is completely baffling, right? It's completely baffling. I'm just going to await the task instead. Okay, so that's the other new keyword. So when I'm making a method async, it will create tasks for me and return them, and I can magically await other tasks in there. And I promise you that it's async. Okay. But you're probably not going to let me off the hook that easy. So I'm going to tell you what that means. What it means is that it's async essentially means when you await something, take the rest of the method and sign it up as a callback. Okay? Take whatever comes next and sign it up as a callback on that task. So sort of do what I did before, but let the compiler do it. That's a first approximation. In a little bit we can talk about a better approximation. But that means that when I execute this method, so let's step through the method. When I execute it, I come in, it's a normal synchronous method so far. It's async, but I'm just executing it like normal. No extra threads are harmed in this experiment. I'm not like spawning something. I'm just going. And then all of a sudden there's this await. And that means, okay, I'm done for now. I can't do anything else because I'm awaiting further information. Take the rest of the method, wrap it up, pass it to that task as a continuation for later, and then return. Return that task that I newed up for, that the compiler newed up for me, to my caller. So now my caller has control. When I get to this await, my caller has control. And he also has a task in his hand that represents the eventual outcome of this method. Then later, when the task I was awaiting there, the download string task async result, when that completes, when I get the string, then take that callback and put it back on the UI thread and run it then. Okay, so just a second. And when that gets to the end, I have a return statement here, and what the return statement is reinterpreted as doing is go up to that task that we return, tell it that it's done. Tell it that I have a result, and everyone who's waiting on it, they wait no more. That's a result for you. Things are done. Okay? And now there was a question down there? Or was that a question about the return?
Where's Matt with the microphone?
Donna, you're sleeping.
Right. So this all looks great, but I have this question about your transformation of download string into download string task async. Couldn't that be have been automated as well?
I suspect that you could have some kind of tool that could automate it, but it really comes down to when you have a synchronous method and you want to create the asynchronous version of it, it comes down to identifying which method calls inside of it have asynchronous corresponding methods, calling those and awaiting those and sticking async on your own method. Right? So you could probably automate this. We haven't tried it, but we talked about it.
And the related redundancy would be, so you have async task of movie. I presume that's redundant because you can't have something async that does not return a task of something.
Actually, you can, so it's not redundant. But I'll get to that in a bit. Let's take one more question and then move on, because we're going to dig deeper just behind you. No.
I actually have a whole pile of questions, but I guess just the most important one right now.
Get only one.
Yeah, these implicit continuations that you're creating, can you have first-class access to them? And
no.
Okay.
And save the other questions for later. Okay. So, can you? The question was, can you get first-class access to the continuations that I create? And you sort of can't, unless you're like super advanced. But what I'm going to do is I'm going to fix up our code so it actually works again, right? And then we can talk about it more. What this transformation is actually about. Now I can do the same thing up here. I just created my own async method. It returns a task, so I can await it, but only if I'm in an async method. Whoa, that was some serious scrolling there. And so I'm going to await it here only if I'm in an async method. So I'm going to make the method async, and I can return the non-generic version of task here to say that, hey, I have a task. It will complete when I'm done, but there's no result. So it's just it's just task avoid really in this ununified type system that we haven't done that. So again, that works out fine. Let's call it load movies async to follow the convention. And then way up here where we call it, we're going to call load movies async instead, and we can await it. And we can only await it if we're in a... So you can kind of see where this is going, right? So async is sort of contagious up the call stack. You return a task, you have to await it, and in order to await it, you have to be async, so you return a task and call it. And that's fine, because you're exposing the asynchrony up the chain, and that's actually what you want to do. However, at some point, you don't care about completion anymore, right? And we are at that point now. I have this event, I click the button, I want the stuff to happen, but I don't programmatically want you to tell me when it's done, When you're done getting these movies, you've updated the UI, that's fine. I don't need to have a handle to your completion. So you can actually make methods that are async void. And then what they're saying is, I'm fire and forget. I don't care when you complete. I just want to kick it off. Okay?
Why did you propagate it up to search button click? What was the point?
Why did I propagate it all the way up?
Yeah, why not just stop at one level further down?
Why not stop one? I could have stopped one level further down. The main reason is pedagogical. So I got to show both the generic, non-generic, and async, and also because I'm going to do some more in a minute if I get to it. So now it should be working, and we should run it. And the experience should be that let's actually take a really nasty year like 2000, before the recession and after it got cheap to make movies. So now you see it's updating while it's going. I can interact with it. I can even press the cancel button, though it's not wired up to do anything. But I can press it. So it's still updating. You can't see it anymore there. That's a really nasty year. I wish I could press the cancel button. Anyway, let's press the big cancel button instead. But so I got responsiveness, and I did it without contorting myself, right? I did it without changing the structure of my code. I just surgically inserted a few keywords. That's great. It's also great that all this happened on the UI thread. I wasn't enlisting all kinds of thread pool threads to help me stay alive. I was just having my execution organized a little differently by the compiler for me. That's really the core. There's one particular thing I want to call out about this core syntax. I keep talking about tasks abstracting over the eventual outcome. When I say outcome, I may mean a result if it completes successfully. But an outcome of executing something can be an exception, right? And that's also captured by tasks. So the task that gets returned from query movie async, if any exception happens in here, the task will wrap that as well. Okay? So an eventual exception will also get bubbled as a completion to the task that ends in an accepted state instead. And the fun thing is, so let's create an exception in here. Let's say if if count, what's the one first? Greater than 0. So on the second iteration, essentially, why do we need parentheses in C#? I always hated that. If first greater than 0, throw new exception. So, come on. What am I doing wrong? Exception, and let's just do it like this. So, if I get through if I get more than one call to this, I will throw an exception. Okay, and let's try to run it. And I'm running it in the debugger. So now I'll go and look at movies, and it's going. Oops, something went wrong. I got an exception. Where does that message come from? It comes from. It's magic. It comes from the exception handler on the calling method here. Okay? So how did that happen? Well, it happened this way. The exception got thrown. It got wrapped up in the task. It got awaited in the caller method. And await unwraps not just successful results, but also exceptions. It unwraps outcomes. So when you await the task, that's when the outcome comes out. It's like you open the box and whatever was in there spills out, including exceptions. And then it gets caught in the enclosing exception. So really, control structure has been restored here, even for exception flow. And that's all there is to it. All there is to this feature in terms of just taking sequential flow and turning it into discontinuous sequential flow, if you will. Sequential flow that puts little chunks of work on a thread, and in between lets other things do their thing. Right? So you can imagine having multiple asynchronous flows going on your UI thread, and it's sort of like collaborative scheduling, right? They'll just take turns posting little bits of work, and whenever they're waiting for something, they get off the thread, other people can get there. In the meantime, you can click and move windows around and so on. So collaborative scheduling here, really without a lot of effort. So I could stop here, but it's actually, this integration with task is actually really interesting. It lets you do fancy things where you start thinking about concurrency as well. And I have no idea how I'm doing for time, but I'm sure that Donna will tell me. 10? 10 minutes, thank you. Okay, so I'll probably stay in the code for the rest of this talk because that's more fun. So I talked about before that tasks are really an abstraction of both I/O-bound work and CPU-bound work. So let's go down here again and pretend that this whole parsing up of the string is really hard work. Like it really bugs our UI thread down to have to do this, and I want to ship it off to some thread pool thread instead. Okay. Now I can use tasks. I can create a task that's CPU bound, and there's a simple API for that. There's an app for that. So we. So let's go look at that. This is a stupid old prototype. I'm not running any of the modern, new, fancy beta stuff. So I'm saying task X, and it should just be task in the new version that run. And that's a simple API that will let me take a Lambda and run it on a thread pool. Okay, no fancy stuff there. I take a Lambda, and this is a Lambda. Just wrap a Lambda around it, and I run it on a thread pool. Okay. So now the work is running on the thread pool. How am I going to get in contact with my result again? Well, it returns a task. What can I do with a task? I can await it. Nice. So now I'm awaiting CPU-bound work that's happening on thread pool thread. I'm awaiting it on the UI thread, which means I'm not going to do more UI work before it's done, but I'm also not going to occupy my UI thread doing it. Okay? Furthermore, I'm going to need the result, so I'm going to need to return the result of this, and I can just return that, and the method works out. Right? So now, I want you to appreciate what's happening. There's no marshalling that I have to do here. I can ship work off to a different thread, however it ends, whether it ends in disaster or in a result or whatever. If it ends, it's going to post that result to its task, and I can pick it up within a wait from some completely different context. Get exceptions rethrown in my context, nicely marshal without me having to think about it, and results come back. Okay. So that is a really useful thing to take load off a given thread. It's also interesting to think about other things like, I don't know if I want to talk about cancellation. We're talking long-running operations here, so we really would like them to be cancelable. There's really not any language feature or task-related feature for cancellation. Cancellation is sort of an orthogonal thing in the .NET framework, but it kind of works really nicely with asynchrony. And the way it works is that you can sort of advertise in your API that you're cancelable by taking a fancy little thing called a cancellation token. Let's call it token. And let's give it a default value so you can choose not to pass it. Default cancellation token here. So a cancellation token is a little signaling device that I can look at it and say, hey, am I canceled? And somebody else can use something called a cancellation token source at the other end to give me that signal. Okay. So I can say, somebody can pass me a signal that I can stare at to see if I'm canceled. And I'm not doing much hard work here, so I'm just going to pass the signal on, and that's how you're usually going to do it. You just propagate it. If it cancels and it gets observed, let's say down in download string task async, then that's going to throw an exception, and that's going to sort of help me tear down the stuff I'm in the middle of doing now. And you can imagine the token getting passed down to multiple parallel things, and they just all get torn down when it fires and you observe it. Okay, so that's why the exception mechanism is good. It can let you don't need to know where you're at. Even if you're at multiple places, it can just tear down stuff. So that means this is going to throw a cancel exception. It's going to get captured in the task and going to get rethrown with the await here, at least if I pass a suitable one to it, and eventually caught here. But we don't want it to write that something went wrong, because you probably canceled on purpose. So let's catch that operation cancel exception and just do nothing if we get that. So we're going to accept that from general exception handling. So what can I pass it? Well, I said that I could create these cancellation tokens by having a cancellation token source. So let's get ourselves one of those. And actually let's call it CTS. And actually, we're going to create one whenever we start an operation and remove it whenever we don't have one. So let's just create a new one here. And at the end of the operation, at the asynchronous end, when we're really done, come on. This is, whenever something goes slow in the new version, we say it's because it's a new version, and when it's slow in the old version, we say it's because it's the old version. But at the end here, I put it as null. So even though there are waits, and this can get interrupted multiple times, if I have a CTS, if I have a cancellation token source, it means I'm in the middle of doing something. Otherwise, I have a null. Okay? So now I'm going to pass the token for that, CTS.token. Token. So I'm going to pass that on. And now all we need to do is actually fire cancellation. Wow, come on. It's a CTP. Now we're going to have cancellation happen. So let's say that when you press the cancel button, you actually ask the CTS to cancel. And then we print something nice on the screen saying status text.text equals canceled. And then we run the thing. If there's no cancellation token source, this is going to go wrong. But, I'm in a rush, so I'm just going to pretend that's not a problem. I still have my old exception. That is true. So thank you very much. I would have to press the cancel button very quickly in order to hit that first. Thank you. So let's make the code actually work again by not throwing exceptions on purpose. There we are. And run, and go for something long. Search, press cancel, canceled. Okay? And it stops doing stuff. You can see that the scroll bar is not growing because the cancellation exception got, passed up. It got through the task. It came all the way out from in here somewhere, got wrapped in the task, got unwrapped, got caught by this exception handler here, and things worked. So cancellation is nice. I'm also gonna just do a little more stuff to talk about, if I have time. I have 5 minutes. Oh, God. So there's a question there. You. Oh, I don't know. Microphone. You can talk into mine.
Okay, so you actually, your continuation is a closure, right? You might be capturing variables.
Right.
And do you So the continuation is a closure. You might be capturing variables. Do you capture them by value or by reference?
We capture them by reference. We always capture variables by reference in lambdas and in other kinds of closures. Actually, I didn't say so, but I probably should. We're not actually capturing continuations like lambdas. They're not really turned into lambda code. It doesn't do a CPS transformation. Instead, what we produce behind the scenes from this asynchronous method is a state machine that knows how far it is in its execution. And what we pass as callbacks is a little stub that says, move the state machine one step forward. But it's still the case that that state machine captures all the locals of the method as fields in that state machine object, and they're captured by reference. Which means that semantics are as close as possible to the synchronous corresponding behavior. Yes?
So why don't you just throw an exception directly? Why do you need this token?
Well, because I'm signaling cancellation in one place, and I want the exception to happen somewhere else. So it's a signaling device. It's a wormhole between these two areas. Okay? So out here, somebody presses the cancel button. I'm in the middle of some work down here. In fact, I'm probably in the middle of waiting, because that's what I'm doing 99% of the time. But it's asynchronous waiting, so it's good. And then at some point, I observe, whoops, the guy pressed, and it may be a little later, right? When it's comfortable for that download string task async method to cancel, it will observe that and say, okay, I'm done. I'm going to throw the exception up. So that's why. Oh, there's such a lot of questions. So let me ask you a quick question. Do you want to see some parallel composition, or do you want me to answer your questions? Answer questions. Okay, answer questions.
So does this work with recursive definitions?
Yeah, no problem.
And what would be your design pattern for showing cancel timeout?
Cancel timeout, that's what I was going to show an example of if that's what you had asked me to do. How do you like that answer? No, but let me say a little thing about it. What I was going to show, there's several ways you can do timeouts, but what I was going to do, I was going to, in the search button click method here, I'm calling load movies async. I can, instead of immediately awaiting it, I can grab the task. Then I can create another task representing, say, a 4-second delay. There's a task, the delay method, that will give me a task that will complete in 4 seconds. Just timer implemented. Now I have two tasks. They're running in parallel. They're not actually doing much work, but they're running in parallel. And then I can call a helper method that combines those and says, when any of these, it's called task.whenAny. You pass it a bunch of tasks, and when any of those completes, the task that it returns will complete. And will give me the result it'll give me is the task that completed first. So I can do that. I can await the result of task.whenAny on that. And if that turned out to be the delay task, compared by reference, simple logic, hey, the delay task was the one that completed first, which means I timed out. And then I can do my timeout thing. There are also more direct versions of it, but this one's more fun. Okay.
So I'm guessing that probably answers my question, but the run any or similar constructs can create tasks that can be used to re-implement synchronization. So if I want to wait on all tasks in a task group to complete, there's some method that creates.
Task.whenAll.
Okay.
And again, task.whenAll is not actually waiting. It immediately returns to you a task that completes when all of those tasks is complete.
So all that work is still happening on the same thread, and
yeah, it doesn't do any threading for you. You can, as I showed you, you can deliberately kick off tasks on other threads, but none of this task stuff and await stuff in itself introduces any new threads.
All right, so we're actually going to shorten the panel. We realize we don't need a full hour and 20 minutes, so this will increase the length of our break, or Mads could take questions for 5 more minutes or show what he wants to.
Oh, I really want to break. No, I'm going to take questions.
All right.
If it's okay, then I'll take more questions.
So,
sorry, maybe I missed it, but did you check the cancellation token at some point? Don't you have to poll to see whether...
I could have done that directly myself. I was being really lazy. I was I passed it on to someone else to do it. So I passed it on. Let's see further down. That's the best trick is to pass the buck to someone else, right? The one that's actually spending most of the time, asynchronous spending of time, non-blocking, but still, is the download string task async. So I'm just passing a cancellation token to that. I could have said, after that, I could do an extra check saying token.throw if canceled. And that'll throw the operation cancel exception if that token was signaled. That's typically the way you want to use it directly. But that's only if you sit in your own loop and you're doing some stuff that you want to be reactive to cancellation on, then you would do that. Otherwise, just pass the buck. Yeah.
Can you say a little bit more about how this is compiled? It sounds like, so once you specify a method as an async one, it becomes, it's compiled specially. So the activation record becomes like some state machine state. And,
exactly.
Okay.
Exactly. So let me just quickly go to the PowerPoint, go to the slide that tells you how it really works. I'm going to skip the one that tells you, that sort of implies that it's really turning it into lambdas. So that's easy, right? I take some code and I turn it into a state machine, and that's what it looks like. And it's an ugly piece of code, but it has certain nice invariants about it. One is that the user code, apart from the awaits themselves and stuff like that, the user code is in there in the same structure that it had before, right? So it's all done by switching on top on what state am I in and jumping your way to the right place. And that way we have confidence as implementers that exception handling and finalies and all that kind of stuff really works out. Whereas if you do a CPS with full CLR semantics, trying to unfold exceptions and finalies and all that, you're going to have all these quirky corner cases that aren't going to work out quite the way you expect them to. So it's really just an elaborated version of the original user code, implemented as a state machine with a switch, or in this case an if, because there's only one await, top, and with a wrapping try catch that catches any exceptions and sticks them into the task and stuff like that. Return turns into complete the task. So straightforward, really, just implementation details. Okay?
Can you tell us a little bit about the lifetime of these suspended objects? Like, can you memory leak these things?
Oh, yeah. But you memory leak them in the same way as you memory leak anything else, by keeping a reference to them somewhere, right?
There's no first. You don't have these things first class. So I mean, how do you hold on to them? How do you even reason they're alive?
Well, so here's how you can memory leak something. If you sign up callbacks to something that never completes, then those callbacks will keep sitting there on a list and never get exercised, and that's sort of a memory leak. The state machine objects themselves, I mean, they live as long as there's a reference to them, which means typically as long as there's a callback signed up to reignite them.
You might need to describe the sync context if it helps.
I was hoping not to.
All right, so I guess if you have more questions, try to corner Mads at some point. For now, we'll take a break, and thank you for this great presentation, Mads.
Thank you, Donna. Glad you liked it.